Good afternoon, everyone. Let me formally welcome Dr. Ashish. He's been working with ST Microelectronics India for more than 20 years now. And, with the conversation that we were just having, you know that we go back a long, long time. He obtained his PhD from IIT Delhi in 2017. And before that, he did his MTech in solid state technology from IIT Kharagpur in 2000. His major area of interest is circuit design, with a larger emphasis on memory circuits and systems. He has more than 17 patent grants up his sleeves and many more already filed, which will get granted over time. And he also publishes quite prolifically in various international forums. So today he will talk to us about, you know, uh, safety and how safety is important for us for automotive applications, for example, and other applications, and how do we make circuit and architectural changes to bring that safety into the embedded memories and therefore at the system level. Okay, so let's welcome Ashish, and over to you, Ashish, with that.
Good afternoon, everybody. So, let me introduce you with the topic. The topic is circuit and architecture for safety critical embedded memories. So, many of you might have well understanding of SRAM memories and ROMs and maybe other memories as well. And when I say about safety or security, what does it mean? First, we will have to develop an understanding of that, what we actually intend to embed in these memories as a function, as a capability, when we say safety and security. So this is the outline of this lecture. So first, I will introduce you with the context and then for the need of a safe and secure memory and how we design a robust memory for low failure rate and how the data theft and static memories take place, and safety and security, specific safety and security circuits implementation in static memories. And we will take up your questions, your doubts at the end. So, so this is important considering a robust operation for safety critical applications. When we say safety critical applications, first think about the automotive application. And also you think about the banking applications, your credit cards, your debit cards, and your online transactions, everything. So do you think that there is a need to have a secure or safe transaction at each and every step for both these domains? When you are driving a car, you need to be safe. You don't expect any particular function or electrical function or mechanical function to break down, risking your lives, right? Or you putting you in trouble in between when you are traveling. And same is true for the banking transactions. You don't want your data, your passwords to be hacked, your account to be hacked. So these are the two major domains where we need to be very, very sensitive for implementing security and safety. This is a very contextual word where you call safe or secure. Now, there has been efforts to address both aspects through software as well as through hardware implementation. Any system is basically comprising of an interaction of software with hardwares. And on top of that, a system is developed. So there are many, many implementations where software algorithms take care of the safety and security aspects. And for those areas where a very high level of security is required, you need to augment with hardware as well, specific hardware implementations as well. So these automotive safety integrity levels, this is called ASIL, This is a standard basically, ISO standard, and ISO 26262 covers the safety aspects for the automotive segment. So when you are now talking about the autonomous vehicles, right? We all are talking about the autonomous vehicle, driverless vehicle, smart systems, and all those things. Then definitely a sense of fear comes into your mind, and all of you are compelled to think how this will be successful in Indian context. Although this is being tested successfully at say a global level, but definitely the complexity of implementation and the risk of implementation is in everyone's mind. Every one of you is considered that there is no driver, how the semiconductor chip or the how the AI will be able to address the address the safety aspects. Like if somebody comes suddenly in between, how the suddenly you can apply the brake, or in a crowded marketplace, how the vehicle will move and all and all. So, or if the vehicle is moving at a very high speed, how this will take care of the surroundings when suddenly something comes flying or there is a pothole in the road. So there are many aspects which needs to be addressed when you are talking about autonomous vehicles. So there also you need to augment the system with the multiple sensors and artificial intelligence embedded around those sensors. So if you have any relevant questions, please do not hesitate to stop me in between. Definitely at the end we'll take questions, but in case something comes into your mind in between, you can ask those questions so that you do not forget it later, and everyone can address and come with a consensus understanding. Now, what is ASIL? Automotive safety integrity level is basically categorizing the safety standards with respect to four considerations: the particular function, the probability of exposure, how much it is exposed, the controllability, severity, and these, the addition of these three, the combination of these three is basically deciding with respect to the ASIL standard. In case there is a threat of life, if some particular function like the brake function failure is going to be a threat of life, definitely this should follow the highest level of safety standard, that is the D. D is the highest level of safety standard and A is the least one. Now coming to memory, we could understand and appreciate the requirement for a safety function, inclusion of a safety function in the system. But when it comes to memory, what role the memory plays and how this memory can be addressed, or how the safety or security functions can be incorporated in memory. So all of you know that the any operation or any execution command that the microcontroller takes, that takes by reading and writing from the memories itself. So in case there is a failure or there is some error in the controlling board or the control itself, then the controller might misbehave, and this will result into a security or safety failure. Like say, I would say sudden unintended acceleration. If you have not pressed the pedal of your wheel, the accelerator, and still there is a sudden acceleration that might be caused by some say bit failure, or maybe some ACR or some other failure phenomena exhibiting by the memory. Now, failures of airbags on the impact, the airbags are expected to open and save your life, but in case this failure occurs, so all such phenomena needs to be very robust in order not to fail, and the overall system together need to address these aspects. Collectively, they need to be compliant enough together to address the phenomena they are required to operate. And similarly, the financial transactions hacking can also be taking place.
Excuse me, sir. My question is, when we talk about safe and secure memory, does it related to the hacking of the memory, or it is its robustness of the memory?
Can you be a bit louder?
When we talk, so when we talk about the safe and secure memory, does it is related to the hacking of the memory? The memory can be hacked, or it is related to the robustness of the memory?
What is the ultimate impact? When a memory is hacked, the hacker can perform the intended operation that is unintended for you. And if the memory is not robust enough and there is some bit failure, then that also can perform some operation that is not intended for you. So both are equally important. If
Okay,
an
okay.
SOC, if a system misbehaves, the underlying cause may be anything. That is a safety or security compromise. So both thing needs to be addressed on equal footing with equal importance, and that is a very important aspect of memory design. Sometimes or many times we do not focus on both the aspects, and there comes the weakness or the loopholes. There the safety features or the actions can be compromised. Later on, when we'll progress in the discussion, this thing will be more clear to you. Okay.
Okay, thank you, sir.
So that's why the third line, when I am saying these issues should be addressed with respect to a robust memory design and also a system in place to detect a failure in case of this happens. Uh, Say POAPs, physical uncloudable locations, are a feature, a very important feature, and that is implemented using SRAMs in order to implement safe coding, a random code generation that can be used internally within the hardware and will not be known to anybody outside the world. And this code, if that is hacked, then this aspect of safety has no meaning, right? So you all of you know that SRAM, when powered up, will behave in a random manner. The initialization of the SRAM. You understand this thing,
Yes,
right?
yes.
Yeah. So because when SRAM is powered up, when the chip is say at no supply voltage, zero supply voltage, and you are powering it up, then depending on the process mismatches that are present in the within the six transistors of the memory cell, the cell is expected to powered up in a specific data condition, either 0 or 1. But this is perfectly random, cell to cell, chip to chip, everywhere. So this is an example of pure random code.
So,
Yes,
so you're saying ki, like hacking while reading the memory, like in the last slide you were saying, yeah,
yes,
the data is stolen while reading. So like you are saying ki the hacker hai, they are probing the ports outside the memory.
yeah. I'll come to that, how that
Okay,
is
okay,
done.
okay, sir.
I'll
Thank
come
you,
to
sir.
that, and definitely that is the case. This is done during the reading. One, the memory is being accessed by the CPU. During that access, the hacker keeps a vigil on the data path and tries to read the data. What command is being sent to the CPU? CPU and in what sequence?
Oh,
Yes.
so am I audible? Hello.
Yeah, you are audible.
So let's say I have a cache hierarchy kind of a thing, and you some like hacker plans a side channel attack on it, and you kind of you read the hacker would try to read the data and all those things. So would it be kind of visible? I mean, it would not be in a way visible to the victim, right? I mean, what data the hacker has read from the memory or something like that. So uh, what I mean, there are some ways to detect those failures, those thefts, right? There would be some ways, right? I mean,
Yes.
in general cases, I'm what I feel is that they might not be visible to the victim, right?
Yeah, you will not be knowing. That's why you are not supposed to protect the operation of the memory or the SOC or the complete system. And you cannot. This is not in your hand. This is in hacker's hand to hack the data. And this is in system that is operating in systems architecture's hand to prevent from such attacks. You cannot take any action on that. When you are a user, you cannot do that. Prevention is not in your hand.
Okay.
That's why these features, these security features, the safety features are bound to be integrated in a combination of software and hardware. Either hardware should detect this or software should detect this. Okay.
Yes, sir. Thank you.
Okay. Where were we? Okay, fine. So a robust memory with extremely low failure rate should be targeted for safety critical applications. That is the inherent failure rate. Inherently memory, how the memory can fail. Inherently memory can fail due to multiple reasons. I have listed few of them, like say process variations that are not properly accounted for in the design, soft error rate, robustness with respect to single event latch-up, high temperature compliance. That means they should be working fine at high temperature and should not fail functionally, and robustness with respect to the aging of the device. So you understand all these 5 points, or should I explain all these points? Okay, let me briefly
Yes,
explain.
yes,
Okay, so soft error rate is understood by all of you. This is a phenomena where the bit cell flips by the radiation. From where this radiation comes? This radiation is present in environment all the time. Maybe differently from place to place, environment to environment, but some amount of radiation is always present everywhere in the form of cascaded cosmic rays. So you understand cosmic rays. So the cosmic ray showers are mainly responsible for these soft errors, and then environment and the chip package. In chip package also there are radioactive elements, and those radioactive elements emit some radiation, and those radiations pass through your memory cell and may cause a failure. And then with respect to the single latch-up phenomena you must have studied in your CMOS courses. So when the chip is operating at higher voltage and also at higher temperature, then particularly this phenomena occurs when there is a very high DC consumption in the chip and the chip altogether fails to operate. Or sometimes if the magnitude of current is not very high, the chip is localized, this may result into the random failures. Then high temperature compliance. At high temperature, you all understand that the ion of MOS device decreases, and this decrease of current should be well considered when you are designing a memory, the chip should be validated in CAD and also on silicon at high temperatures. And similarly, for aging, you should test your chip with respect to the required timeline. If you want to use a particular product for say 20 years or 10 years under certain environmental conditions, like 140 degrees Celsius, or for automotive now this is 175 degrees Celsius, then under that conditions with accelerated aging instrument methodology, you need to test your semiconductor chips that yes, there is not going to be any failure. If that is not done, then at certain point of time, your semiconductor device, your car, or maybe your very critical biomedical applications like say pacemakers or human embedded semiconductor systems can start malfunctioning, and that can be life threatening. So validating your design with respect to aging of the device, and aging is a prominent where aging, when you say aging, this is basically NBTI. If you understand NBTI phenomena, this is negative bias and temperature instability. And what this phenomena does, this phenomena slows down the device, increases the VT of the PMOS primarily. Certainly, this is also present for NMOS, but at less severity. So, when this aging phenomena is present and you have not validated with respect to aging, then after certain lifetime, your product will start malfunctioning within the required lifespan. I think whatever I said is clear to you. If you've understood all these things, we can go ahead. If any doubt, you can ask me right now. Okay, good. So for any failure occurring, there should be a mechanism to detect and take a preventive action. And what all these preventive actions can be done? Those can be taken at the design step, or those can be taken at when the system has failed, or the component has failed, and you can take a preventive mechanism, a provision to prevent the system failure. Like if your memory has failed, your system, if the system is able to detect that yes, your memory has failed, you should be able to, or your system itself can be able to take a preventive mechanism. Like I would say, when you try to log in a banking system by say your wrong password, what happens? This allows you five attempts, and after that it locks the system that you cannot attempt anymore for a particular duration. So this is a safety mechanism put in place by the software. And similarly, there can be safety mechanisms placed by the hardware as well. And the hardware detects a fault. That is, if the RAM is failing and the hardware is able to detect, yes, that the RAM has failed, the data read is incorrect, there is an intrusion, then there can be a hardware reset. The system itself can trigger a hardware reset and prohibit the further operations. This can lock the device. So this sort of safety mechanisms are also very important to consider for such applications. So few points I have listed here. Use of appropriate assist circuits to ensure functionality and robustness, so that with respect to environmental drift under standard operating condition, you do not frequently face a safety issue, a failure, a reoccurring failures. Then an stable and robust process technology. This is the thing to be addressed as technology as well. Like SCR is completely dependent on the process technology. The way you define the resistivity of your well, the way you design the process steps of your MOS transistors will also decide what would be the critical charge required for an SRAM cell to be flipped. And if that critical charge required for the SRAM cell to be flipped is higher, definitely your memory would be robust. An adequate design margin to address the design PPM. The design margin, you all understand that when you are designing, you ensure a certain level of differential at sense amplifier. That is the simplest and easiest example of design margin. So there are multiple margins. There are multiple margins to honor in the memory. And if you have kept a margin, keeping a view of the safety or the security aspect that may occur under certain environmental conditions, then this will help for a more safer semiconductor or system design. Then design device aging consideration during validation. Validation using stressed conditions like aging or um, and specific high voltage spikes are applied, and under that conditions the functionality of the device is checked. Then redundancy and repair capability in memory is a very, very important aspect. The failure what we are going to talk about are, in fact, most of them are rare failures. And when such failures occurs, the memory or the system in itself should have the capability and provision to repair itself. So, suppose you have designed a memory of say 4K words, and you have got a redundancy of say suppose 48 words or something like that. Then in case your memory fails, then you have an option to replace those failed words or failed bits with respect to the newly available locations that may work fine. And the last one, but the very, very important one, is the transient fault detection and correction. And this is the hardest one to detect and correct. So there is a lot of focus in today when we are talking about, say, ADAS or automated vehicles. This aspect is being addressed specifically in semiconductor design, how to detect transient faults and corrections. You understand what are transient faults?
Sir, they occur for a very less amount of time and then die out.
Well, partially correct. Yeah, they occur for a very short amount of time. But if they occur a very short amount span of time, why this is difficult to uh, put preventive mechanism for such faults? Transient faults are basically faults under external environment um, impacting a particular function of any component, not in a severe manner, but maybe in a softer manner. And that is not going to exhibit at t is equal to 0 or even at t is equal to 15 years. But under slight perturbation condition, this will result into a failure. Like say, if you are having um, a particle is striking a transitioning node that is having say less in capacitance, but that creates a path, a discharge path through the driving NMOS or the PMOS, then what would that result into? That may not result into a full transition, but that may result into a delay in the signal, and that delay might exhibit itself in a failure. So you should have a capability to detect such small delays that may cause catastrophic failures in your system. You cannot delay permanently such detections or put in place a mechanism that is very, very pessimistic for the design, because that will affect the performance of your system. So you need to maintain the performance of your system, as well as you need to put in place the safety mechanism by putting a detection mechanism in place. So that is the essence behind this. So later on, there will be a couple of examples that will help you to understand more with respect to um, these transient faults. So this slide is a very important slide for understanding how data theft is done in static memories. So you see here the familiar SRAM cell is put here. This is your SRAM cell, very familiar 60 SRAM cell. Now, if you see a laser scanning image of the SRAM cells, then with respect to the data is stored in the memory cell, the color of the imaging will differ. So, laser scanning image of the SRAM cell can reveal what data is stored inside the memory. So this is a way when a hacker can do this and detect the stored data. Fault injections is in the photo flash. This is a device, photo flash, for very small amount of time, very short duration, and also in a very focused area. When I say in a very focused area, then this injection of say laser or photoelectrons can be put within a memory cell also nowadays. And usually this is done to probe the data over a span of one IO. If your one IO consists of, say, it's a mux of 16, so within a span of 16 memcells, if one is able to disturb the data that is being read, then he is able to probe your data. So what is done usually in labs using these photo flash, automated system, an automated mechanism is put in place where this sort of attack, random attacks, but systematic. That means these attacks are done a millions of times whenever the data is read for millions of cycles. And based on the fault injected and the data read, ultimately the data content of the whole SRAM array is found that can be determined. So there are dedicated labs and systems put in place. Those who want to hack the systems for major gains by hacking the banking transaction systems and all. You regularly you see the servers being hacked and codes being theft. So this sort of dedicated massive operations are uh, planned or executed in order to break through into the system. So maybe you might be aware only of the software attacks that are made to break into a computer or a systems, but these hardware attacks and the extraction of codes are, and see, I would say, a leap ahead approach to do such activities. So another slide based on that. So this is reflected infrared light backside image of the microcontrollers that is seen here, shown here. So with by analyzing the reflected backside images, the ROM contents are also extracted, because you know that the ROM is basically programmation by either by metal programmable or by the via programmable. So these informations can easily be extracted by the backside reflected infrared imaging. Now, what are the safety and security implementation in static memories? I would list down a few of those here. So, word line fault detection. The first one is that is the very widely used methodology is to use the word line fault detection. So, this scheme aims to detect any deviation from normal word line selection. Like in a memory, how does a memory operates? Let me come to this section here. So if you'll see that basic say functional diagram for a memory, this is your core region, this is your control region, this is row decoder region, and the red one, this is the highlighted one, is the one word line here. This is the one word line. Now, when you are accessing your memory, what you are doing, what you intend that only one word line should be high. What will happen if two word line gets high by any fault within the memory or by any intrusion, outside intrusion? If two word lines are selected, can any one of you guess what will happen if two word lines are selected at a time?
So corrupt data will be read. Multiple bits will be like multiple bits will be activated at the same time in the same row, in the same column. I mean. I was saying कि like
Well,
yeah, same column में अगर multiple bits on हो जाएंगे तो उनका data correct हो जाएगा and output पे will have wrong data.
see, word line is selecting rows,
Yeah.
right?
Yes, sir.
Not column.
Like if multiple rows are selected, then like if in a single column, multiple rows are selected, multiple bit cells of different, you can say, rows are selected, then their data can be read wrong on the bit lines.
Why?
Because it's okay, so you can say like two cells, I'm reading from two cells and the same column. Then
Yes.
when their bit line will be sorted to their internal nodes. So if both the cells have different data, then we'll not know कि like मेरी bit line कौन सा like discharge उसका सही से नहीं हो पाएगा.
Right, right. Perfectly right. Very good. So your data will no more be the valid one. This will be randomly corrupted. So there should be a mechanism, or there is a mechanism usually put in place to detect such issues that occurs during runtime of the memory. Then use of parity bits, use of ECC, weak bit detection and replacement, use of backup latches for safety critical nodes. Now, word line fault detection, I think the essence, what we do and why we do, that is clear to you. Details of how we do, I will come to that. I think use of parity bits at this point is should be understood by you because you might be studying in your courses also, right?
Yes, sir.
So through parity checks, you want to ensure that the word that is read, that is correct or not, right? Assuming that your parity bit is not correct. Then comes use of ECC. ECC is error correction code. ECC is just an extension of a parity bits the way this is implemented, and ECC also takes help of the additional bits in the word in order to assess whether the read data is the correct one or not. So when you write into a memory, say if you have a 32-bit memory you want to use, then you will have to use a 7-bit parity, 7 additional bits for ECC, and these ECC bits, while writing into the data, say locations, while writing this word, you will also write these ECC bits, and during read, you will have a recalculation from the read out data and matching with this, and this will help you to find out whether the read data is correct or there is any fault. This is a standard practice. ECC might be known to all of you, and this is a very, very powerful tool today to detect any fault, mostly single bit faults. ECC is used mostly to detect single bit faults. Because when you go for, say, detecting multiple bit faults, why don't we use this? You understand this thing? Why ECC is usually limited to single bit fault? First of all, you understand ECC?
Yes, sir.
Okay. Then, if you understand ECC, then you must be knowing that ECC is usually used for detecting single bit faults or at the most 2-bit faults, not more than that. Where comes the limitation? Why can't this be used to detect if you are using a 32-bit memory, then in all the bits are faulty? Why can't we use to detect a 32-bit fault? This is because the hardware or the complex, complexity in the algorithm that will lead to explosion in area of the memory. So area is a very important aspect whenever you are designing a memory, and whatever features, may it be safety, may it be security, or may it be a low power feature, whatever you are implementing, you have to be very, very much vigilant not to impact the area too much. And that is the reason this is limited to 1 or 2 bit fault detection. Then weak bit detection and replacement is another concept where we detect the bits that can fail marginally, and we intend to replace the access to these bits before they have failed. So what is the difference between redundancy and this? The same set of redundancy can be used by the weak bit detection as well. This is a preventive mechanism where you don't wait for the failure. At t is equal to 0 itself, you find out the weak bits and do where possible corrections. And with this correction through weak bits, your system will be much, much robust for its lifetime. So this is a extremely relevant concept, and is also being used in multiple places to make the system robust. Then coming to the use of backup latches for safety critical nodes. So for say for latches, there is a threat of failure due to radiation, right? Or due to high leakage, localized high leakage due to the random process variation or say any fault present in the latch at process step maybe. So a backup latch is used for safety critical nodes. When you say backup latch, it means you are using 2 latch instead of 1. Simple. And then the fifth one is use of dummy bits to ensure correctness of read data. What is the use of dummy bits? Does anyone understand? You have worked a lot on memories, but do you understand what are dummy bits? Okay, so basically, when you read a memory or write into a memory, what you do? You start from the address and then clock. Now, after that, there is an internal decoding, the row decoder selection, then sense amplifier triggering through the dummy column, and then data readout through the IO. So there is a sequence of event that needs to operate in a disciplined manner in time domain to ensure that the correct data is read. And dummy bit, when I say use of dummy bits, you place one column of data, additional column of bit cells for 1 and one for 0 in order to observe at every read and read operation, whether the read out data is correct or not. The dummy one that you are intending to read, the cell is hard programmed as 1, and for dummy 0 what you want to read, the cell is hard programmed at 0. So there is no question of reading 1 from a column which is intended for dummy 0 and vice versa. So this mechanism, this arrangement is kept in memory just to ensure on each and every access of memory, each and every read access of memory, to be very sure the integrity of the operation. Suppose there is some intrusion at some particular place by external means, then the timing would be wrong for the sense amplifier triggering, and the read out data would be wrong. This is not a definitive check, but yes, every safety aspect put in place in hardware has a probabilistic coverage. When we talk about placing any safety or security feature put in place in hardware, we talk about probabilistic coverage, 50%, 90%, 100% overall coverage. So no detection is 100% foolproof. Now coming to the ROM code encryption. Next one is shielding of important nets to prevent from external probing. Shielding of important nets. So when a hacker is trying to read, like here in the say backside images, suppose you are having a programmation layer here, or say data being read out here, and on top of that data, if you put a shield of metal, then that would mask the observation of the hacker. This means if you see this is the backside image, and if you are reading out a data and that data is traveling in metal 1, then you cannot shield it. So in order to shield the data, you must use one level higher metal, that is say metal 2 or metal 3, in order to read out the data, so that you can use the lowest level of metal that would be coming as the picture and the backside images. So usual practice is always to use the lowest level of metal in order to avoid the congestion in SOC where the safety is not required. But when this is a safety or security critical application, you must use district, you may use district to enhance the safety coverage of your memory. In coming to ROM code encryption, I think encryption, what is encryption is known to all of you. We encrypt something because we want to not to disclose the actual thing. And when the raw matrix is being programmed, raw matrix is being programmed in hardware. When you read out the ROM data, you decrypt the read out data and then use it for the system, for the CPU. So that is the mechanism put in place so that even if the hacker has read out through these backside images, or even at the boundary when you are reading out during actual operations by such laser voltage probings, then also this encryption will help at hardware level to prevent user from understanding the actual content or the actual code that is required for the CPU to operate. So next one will be the monitoring of critical signals for correctness in each cycle. I just explained to you the dummy bits. The dummy bits are taking monitoring the complete path from clock to queue. Similarly, the individual signals, like say the internal clocks or the decoded address signals or the maybe any other control signal when that is the sample like chip enable, that can be sampled out, reverted back from this point, at this point, reverted back and latched at this here. So during each and every access of the memory, just like you read out the data, you sample the queue, you also sample these signals. What are the values? Suppose during an actual operation, you expect your internal clock to be in the low condition. And when you have taken out the external clock here and comparing the external clock is coming out to be 1. Then you should understand that there is some problem within the functionality of the memory, within the signal flow of the memory, and the raw data should be discarded. Understood? And then use of deep NVL to avoid single event latchup. Now, let me progress with the, you understand why deep NVL is used for mitigating latchups?
नहीं आशीष, इनको डीप एनएल के बारे में नहीं पता होगा.
Okay. So for latchup, you understand the underlying reason behind this, right? The underlying reason is what is the underlying reason behind this latchup? Right, because underlying reason is just the triggering of a thyristor where the PNPN formation is taken place, and due to the high resistivity, the feedback resistance that is quite high. I think I must have some diagram as well. Sorry, I don't have. So the effectively feedback resistance that is there, we need to reduce that. In case we are able to reduce the resistance of the well, that mitigates the PNPN triggering, and your latchup phenomena is nothing but the PNPN triggering. So now coming, what is the time left? Anuj, can you just remind me?
So Ashish, it's 5:30. We can go on till 6, even 6:15 if you wish to.
Okay, fine. Perfect. So so now I would explain the way the word line fault detection is done in memory. You see the word line. These are the word lines. The red lines are the word lines. So this one is the selected word line, and here we put a raw matrix. The raw matrix, basically what this raw matrix does, this raw matrix encodes the word line address, and this encoder section, and from here this comes the actual addresses that are coming here. What you want to do, you actually want to detect wrong word line is selected, no word line is selected, or multiple word line is selected. In for all the cases, what you do in this way, this is the encoder section. This is the raw matrix, and with the help of word lines, the addresses are encoded. So this is a separate hardware added. This is a separate hardware added. I have also given a reference to one, say, US patent here that may help you to understand the detailed architecture of this one for more understanding. So this is the hardware added, additional hardware added to detect word line fault. And after once these addresses, the selected word line address is encoded, what is the next step? You need to compare with the actual addresses. And when the actual addresses match with the encoded addresses, this means everything is fine. So a signal comparative output is kept as a cell okay, selection is okay. And at each and every access of the memory, this particular cell okay is monitored for its correctness, for its expected behavior, for its expected polarity. So cell okay, in case you expect is to be say high, then at each and every say read access, this has to be, or write access, this should be detected as 1. And in case this is detected as 0, this means for this particular access you have a fault and you need to abandon this operation, this particular cycle. This point is clear? You understand this method of detection?
Yes, sir.
Right? So this way, this is the detailed logic implementation. Anyway, I will share the slides with you. So the detailed, these are the logic arrangements. These are the comparator logics, where the input address bus and the encoded address bus. This encoded A bar bus is basically is from the encoder logic, from the raw matrix that you have derived. And these two are compared in order to arrive at a conclusion whether the address, that the word line that I selected was the correct word line I selected, or that was the faulty word line I selected, or that was none of the word line was selected. Similarly, for critical signals, like say internal clock, I just explained you. So you sample you latch the internal clock in the control region, and then you take it out. You take it out, these signals, say in the control region somewhere here, and then you compare it with the expected behavior. So what these safety mechanisms are doing, actually they are not doing nothing but double checking whether the input what you gave has been disturbed inside the memory by any means, maybe internal or external or not. So the integrity of signals, that is very, very vital for the correct functionality of the memory, that is ensured by these detections and comparisons. And similarly, that is with respect to the any other input, any other critical input that you want to monitor, or with respect to any other decoded addresses like the mux addresses or row addresses. If you want to make sure with respect to the expected behavior, this can be extended to that level. But the concept is that you double check by sampling these signals outside memory and comparing with the expected behavior. This is the same thing, the next level implementation of the internal clock. This has been taken out as the CLK out. Now coming to duplication. Duplication is a very important thing, like say self-time. You all know that these memories, particularly the larger instances where the speed is required to be extracted from the memory, use sense amplifiers, and in self-timing path there can be errors or there can be fault injections in the self-timing path as well that may trigger random failures for the whole world. So if you can detect that if there is some intrusion or the problem with the say dummy path or the self-timing path, then you can take a decision. So duplication is done in order to prevent the misbehavior of your system, even if there is a attack on one of the self-time branches. So in fact, you duplicate the self-time branches by putting two dummy columns separated by a distance. As I told you that the laser impressions can be smaller also for attack and can be very, very wide also for the attack. So in case there is a laser tag of a wider footprint, you need to take also into account and keep the separation between these two critical circuit components far enough so that if one of them is affected, other is not affected, and this will ensure the uh, duplicated one will ensure the correct functionality of the memory and system. So now coming to the another very important thing, that is laser shoot detections. These are all with respect to say dummy bit tracking. So dummy bit implementations in the RAM and ROM, the way you do, you embed one dummy bit and you do implementation and sense out the dummy bit in each and every read cycle. The details of that, what I explained you earlier, is demonstrated here. So this is dummy 0, this is dummy 1, and these two blocks are embedded here in the memory, integrated with the actual block, and in each and every axis, these are validated for their correctness. Now coming to a very important part, that is the column error detection, or you see laser fault detection. So now when you do a laser injection in order to corrupt the memory or to introduce a random behavior in the memory, then what actually this laser does. So you must have heard about these laser faults introduction in the memories or in SoCs or in chips. But what does this laser does? Do you understand the basic phenomena behind that? Anyone? Any idea?
Sir, update the content stored in the memory.
But how? Obviously, the intention is to corrupt the memory. Then what is the mechanism, expected mechanism behind that? The expected mechanism behind that
So what?
is
So can I try? So what I feel is that the laser, targeted on the device or PMOS or an NMOS, let's say, specifically targeted on the OD region or the active region, would on the N wells or the whether basically the doping has been done for the source and the drain. It would try to target the laser would target that region, and it would try to change the operating region of that device. So I mean, in a way, maybe moving it from linear to saturation somehow, and then forcing the value at the Q and the Q bar node to get changed for an SRAM that ways.
Uh, for sure, laser attack is capable to do that, but the primary phenomena that occurs is the emission of photoelectrons by laser. The laser basically excites the electrons and helps create, uh, I would say, avalanche of photoelectrons. And these photoelectrons, say, if this is N plus P junction, that is, if you are forming an NMOS, then there is an N plus P junction. So there is a reverse bias at that point. So what this does, when your net, say your bit line is connected to a particular device, and this photoelectrons will convert this P type to N type by a avalanche of photoelectrons, and there will be effectively a short circuit of bit line to the ground. This is the primary phenomena, that this is basically creating an avalanche of photoelectrons, creating a short circuit with ground for any net that is connected to that particular device. And if your bit line is pre-charged, and if you are supposed to read a non-discharging location, then this avalanche of electrons, this laser shoot phenomena, will deliberately cause the bit line to discharge. And what you will read ultimately will be a 0. Understood?
Yes, yes.
So to detect this phenomena, what is done? Uh, a patch of diffusion where you have put a metal, connected a metal through contacts, is placed as a probe. And when a fault injection laser attack comes, what will happen? This probe that is kept pre-charged, this blue line metal 2, similar to this is the actual bit cell, right? This is the actual bit cell. In the neighborhood there are array. And in between there are these sensors. I would say these diffusions are acting as sensors for laser attack. So in between these sensors are embedded, and these are sensing if there is any attack or not. If there is no attack, then this particular metal to line will always be pre-charged, and you will always read a 1, a non-discharging condition. But only when there is a laser injection above a certain critical threshold. Now, the width of this patch has to be in accordance with what level of injection you want to detect. And based on that, this width and frequency is decided. Frequency is decided based on what is the extent of impression of attack you want to cover. So this one would read as discharging case, 0 case, if you are having a laser shoot. So as soon as this data is read as 0, the system flags error into the and prohibits the further operations, or can take any operation it wants to take to prevent the consequences of the external attack. So the important thing is to prevent the consequences, the bad consequences of these attacks. So this is the mechanism, a very important mechanism that is placed for such systems, and this is particularly useful for the smart cards, where say payment transactions and all are done, also pay TV or something sort of that. So in such sort of projects, semiconductor system, this type of safety system is put in place. where a hacker can simply take the card at his home and do experiments, break the code, and again go back and use these to at the online system or at some machine and have access to the money or any authorization. So this is the way this is implemented. This is distributed, chained IO, like these are distributed like this. And a common signal is basically uh, ORing is done in order to have a final decision at chip output level, because these detectors are spread across the horizontal segment or the IO segment of the memory, and the final decision is an ORing of these expected lines. This is just the timing diagram to show that what is the expected behavior, and during fault injection you see this is going down. During fault injection, this is dead last. This is a detection signal. This is going down. And when the injection is finished, this line goes up. Now, parity bit, I already talked about the parity bit. Maybe this is quite understandable. We use parity bit in order to detect any flip. Definitely assuming parity bits are himself not spoiled or corrupted. Column encryption. This also I explained, although not with these pictorial representation, but yes, this is a specific case of say encryption where the column inversion is done. Whatever you write, if you want to write a zero in your actual code, you write a one and vice versa, so that the hacker that reads out the data will not be able to understand the correct code. Uh, Going a step ahead, these inversions are programmed column wise. See, if you are having say 4,000 columns in your ROM matrix, in your ROM cut, you can randomly choose which column to invert and which column not to invert. And this information would be programmed through metal programmation in the IO part, so that during the readout, you can read the correct data. But the hacker will not be able to decipher the ROM array by just backside imaging. By understanding the metal programmation, the hacker will not be able to understand what is the ROM content. Understood this point? Okay. So just an overview of soft error mechanism and prevention. So soft error, all of you understand what is the mechanism of the soft error. So see, this is your 60 cell, two are missing because they are not playing a role in the soft error. So for the demonstration purpose, these are the four transistors of the 60 SRAM cell. And you see the responsible transistor, I have expanded it, and you see that the injection, this bipolar effect takes place, and this triggers a current between these two. So this is a 1. This 1 means this transistor should not conduct in order to hold a 1 at this node. And when there is a trigger and this bipolar mechanism it takes place, then this transistor is carrying a current, discharging this node, triggering the flipping of this bit cell. Understood? So this is your soft error phenomena. And the another phenomena also is in place, although this bipolar mechanism I have kept is because this is one of the dominant phenomena for bit cell flipping by radiation. But a more complex phenomena that takes place here is called the funneling. So you may find out some good papers that can explain the detailed concept of funneling, but actually that is not needed at the moment for you. But the funneling phenomena creates a perturbation in this channel, and that perturbation creates a transient flow of current here. By enhanced charge, what these charges are accumulated here by, say, the strike of this particle. This is the particle strike. By the way, I forgot to mention that this arrow is mentioning the direction of the particle strike. That in case is creating the electron hole pairs. And these electron hole pairs are in essentially taking um, uh, are responsible for triggering this MOS device on and discharging this particular node. Many times this is misunderstood that this particular charge is basically responsible to recombine this one and flip the cell, but that is not the correct phenomenon. The phenomena, in fact, it is that this particular collected charge is creating a transient turn on of this device, and that is creating the discharge of this node. So this soft error is measured as a fit failure in time. This is the measurement criteria for the soft error. And one fit is the one upset per 10 to the power 9 hours. So when we are talking about the safety, we are talking about, you can think about how much sensitive these systems are with respect to failures, how much catastrophic even one failure can be there for such semiconductor components to fail, that such distant phenomena in time domain are considered to be the significant enough to be candidate for mitigation. So this is just showing the soft error rate, how this is coming. So for the DRAM, this is much varying with the design rule, but for SRAM, this is trend is quite flat, and this is just due to the difference of failure mechanism in DRAM and SRAM that is exhibiting into a failure. So if you are thinking that if you are at a very high technology node, so you don't have SCR phenomena, you are wrong. This is fairly constant with the technology scaling as well. For sure, now there is a savior with this, that is FDSOI, that is creating almost zero SCR. But there is another slide, the software and prevention. So this is very important to understand how we design memories, and the choice of MUX, how this helps to design a memory that is less sensitive to soft error or single event upset. When we say there is a failure in memory, this means that either one or more bit is flipped or corrupted by the radiation. If none of the bit is, the radio out bit is impacted, then there is no impact. So in a particular MUX, say if you are using a memory with 16 MUX 16, where there are 16 columns responsible to define an IO, to design an IO. Then if you are reading a particular column, say fifth column, then when you are reading out in the, say, another column, this will not exhibit as a failure, but that bit still has, that may have flipped, and that may exhibit in the subsequent section. But how this MUX helps? This MUX helps because if some energetic particle is here, so when this is traversing at an angle, and when this is passing through the semiconductor, through the substrate, the charge that is, this is creating a line of charge basically. Let me see if I have that particular, like this. I can say there is a line, it's creating line of charge along its direction. So as it moves, this loses its energy. And when this has created a defect or a say flip in one particular within 16-bit cell, bunch of 16-bit cells, next 16-bit cells are less vulnerable for this particular strike. So for if you consider a memory in totality, only one bit would be impacted, not the other bit. But if you are having a mux1, then this particular is energetic enough to flip 3, 4, 5 cells. And you will have a multiple bit failures. And these failures will not be able to be correctable by ECC, because ECC is detecting or correcting only 1 or 2 bit failure. So if you have chosen a Mach 16 or Mach 32, depending on the technology and its sensitivity with respect to the radiation and generation of charges, then effectively you are de-risking for this safety or safety aspect through the choice of marks, because this error will be detectable and also correctable by the ECC put in place, otherwise not.
So,
I think,
excuse me, sir.
yes,
The multi-bit errors
yes,
are more prominent in lower technology nodes, where area of the pixel are smaller and a single energy part, the large energy particle can disrupt more cells at a time.
yes, that's true. As the technology is scaling, then exhibition of say MBU is coming as a, although MBU or say 2-bit failure or MBU is a very secondary effect. If you are having say 10,000 single bit failures, then multiple bit failures would be say very less, 10, 20 or something like that, many orders less than that, at least 1 or 2 orders less than that. But yes, you are correct. For lower technology nodes, the MBU phenomena is increasing. And there, the choice of marks would be really very, very relevant in order to prevent or in order to ECC to be robust.
Thank you.
These are something high energy and thermal neutrons with respect to the particle nature, how these are impacting the participating or contributing towards these failures. Not much relevant to you for now for these understanding, but yes, you can go through these details. This basically just since you understand that today the major phenomena of say single event upset is thermal neutrons, because in the energy spectrum of the neutrons, what are thermal neutrons? Thermal neutron means low energy neutrons, and low energy neutrons are contributing more for ACUs. Why is this so? Why is this so? This is the very important thing to understand. Maybe this will help you later on. Not essential, but yes, this is the interesting phenomena. Like low energy electrons, and these are high energy electrons. You see high energy neutrons. So when a high energy say neutron passes through an atom, then the impact parameter is less because of its velocity and the time during which this interacts with the nuclei. You understand this phenomenon, the impact parameter? You must have studied in your modern physics sometimes. So the time during which this interacts with the nuclei on which through which this interacts. That means the silicon substrate, the device, the memory device, the memory cell, the NMOS, the pull downs, the substrate of the pull down through and atoms of silicon through which this interacts, this thermal neutron, the duration is very less for high energy neutrons. So interaction is less, and when these are thermal neutrons, the time during which this interacts with the nuclei, because nuclei interaction is more responsible for the ejection of electron from the impacted nuclei, from the impacted atom. So this impact cross section being higher for the thermal neutrons, the extent of charge generation by thermal neutrons is much more than by the high energy neutrons. And that is the reason these are the point of focus in nowadays in newer technologies to how to reduce this in technology. So there are certain ways like epitaxial layer or a thin crystalline layer. An epitaxial layer you by putting, say, a lightly doped epitaxial layer is used or a heavily doped bulk. So in the channel region, you have less EH pair that will be less severe for the channel, and conduction will not be possible. It will not be able to trigger the cell, say, MOS device on. So this is one, and on this line itself, on this concept itself, if you consider SOI, effectively there is no doping in the SOI technology, in the FD SOI technology, and this helps to reduce the SCR almost completely, almost completely. The action which was taken for the bulk technologies for lightly doped, thinly doped, say, P minus epitaxy, so that is visible in a very prominent way for, and it has come as a blessing for SOI technologies where SEU, SCR phenomena is almost absent. So this is the concept I just explained, that is the proper repeat mux factor in memory. We just discussed this point. So I think I'm finished with my talk. If you have questions, you can ask.
Could you please explain the concept of dummy bit, how it helps in correctness of read data?
Your voice is not correctly audible to me.
The dummy bit concept that helps in the correctness of read data.
Uh, Dummy path, you mean to say?
Yeah, मतलब dummy column is concept of dummy column is clear, but I don't understand the dummy bit that you have discussed.
Yes, yes. Dummy bit. Dummy bit is to check for the correctness of signal flow, electrical flow. The all operations has been moved correctly, and there has not been any intrusion or any problem anywhere, like word line delay, or there is external attack at the word line site, or there is some attack on the pre-decoding line or fault in the pre-decoding line. So anything in the signal flow from clock to data out, from clock to data out, at any step, if there is some problem, maybe internal or external, that will exhibit that may exhibit. There is a probability, not always. If the change has not been up to that extent that to cause the failure, this will not be detected. So this is the probabilistic detection system put in place.
How comparison is being made that read has been done fine in
This
that
is,
case?
see, you missed the initial point. When I am saying dummy one column, then all the bit cells in this column are hard programmed to one. All the bit cells in this column are hard programmed to zero. So that when you read these two columns, you always expect a data one and data zero. So after reading, you are making a comparison whether this particular Q0 is 1 or not, whether this particular Q2 is 0 or not. So that comparison is being made. And through this comparison, if you are finding any discrepancy that dummy 1 is read as 0, this means you have some problem and you need to discard this read cycle.
Okay, okay, got it. Thank you, sir.
Any more questions? So if there are no more questions, then let me formally thank Ashish for taking out time from his busy schedule and uh, joining us on this call, taking the session for us, and introducing us to various uh, safety and security features that we have in SRAMs and ROMs, because they are a field of active research in the industry today. And if some of you want to pursue, your thesis or your capstone projects in this area, it could be a very good idea to pick them up, and then Ashish could be the one uh, co-guiding you on these topics alongside me. So we can think about it, and if there is interest, please do let me know, and we can engage Ashish into being a co-guide for those projects. Thank you, Ashish. Thanks a lot again.
Thanks,
And
Manoj.
it was really good to have you here. And I'm sure students have learned a lot and they would have benefited a lot with this session. Thank you.
Thank you. So I will share the slides with you. You can share with the students.
Yes,
And
please.
for
I,
any
I will then
query,
pass them on to the students.
you can share for any query, any more detailed understanding. You can always share my email ID, my phone number with them so that they can contact me directly. This will be my pleasure to assist them for any type of queries and also for their projects, for whatever good things they want to do.
Thank you, Ashish. Thank you for being so open and supportive here. Thank you.
Okay, thank you. Bye-bye.
Thank you,
Bye.
sir.
Thank you, everyone. Bye bye.